Hey there, STEM chemistry students. This is Ms. Ruark. This is VICAS 3.2, and we're going to talk about how to use moles to determine the volume of a gas or the mass of a gas. Okay, so we haven't covered gas laws yet, but when we get to gas laws, this will make a lot more sense. But for right now, let's just think conceptually. If we have the volume of a gas, that volume of a gas is going to change depending on temperature. So let's say that we were to increase the temperature of a gas. Well, if we increase the temperature of a gas, we're going to end up increasing the volume because the kinetic energy of those molecules will increase with the amount of temperature. As the kinetic energy increases, they'll spread out more. Okay, well, on the flip side, if we decrease the temperature, we'll also decrease the volume. Slow down the kinetic energy of the molecules, they start to compress on each other. All right, what about the pressure? Well, if we were to increase the pressure of a substance, of a gas, we would actually be decreasing the volume because in order to increase the pressure of a gas, we have to compact the gas a little bit more, we have to press in on it. And then on the flip side, if we were to decrease the pressure, we would actually be increasing the volume to allow for there to be more space. All right, so the volume of a gas is usually going to be measured at standard temperature and pressure. We call that STP. Standard temperature is 0 degrees Celsius, and it's at 101.325 kilopascals. This will make a lot more sense when we get to gas laws, but we haven't done those yet, so it's okay. Just put that on the back burner. But we definitely need to know the 1 atmosphere and the 0 degrees Celsius. Okay, that's standard temperature and pressure conditions. All right, so at standard temperature and pressure, 1 mole of any gas will fill 22.4 liters, and that's called the molar volume. 1 mole of 1 liter, or 1 mole is 22.4 liters, so that's the molar volume of a gas. 22.4 liters of a gas is equal to 1 mole, so that means that it has to have 6.022 times 10 to the 23rd particles, because 1 mole is equal to 6.022 times 10 to the 23rd particles. Okay, molar density. Density is equal to mass over volume. Okay, now because we're messing with really small things, we'll typically do grams per milliliter. When we're talking about molar density, however, we can use in place of grams, in place of mass and volume, we can use, because it's molar density, we can use molar mass divided by molar volume. Now, the nice thing about this is that the molar volume will always be 22.4 liters, always. So the only thing that will change is this part right here. And it changes depending on what the substance is. All right, and we don't have to worry about this because I'm not using T-tables, but I left that in there, so I do apologize. Oops. Okay, so the only thing that you have to worry about changing is the molar mass at the top. All right, so let's do some problems. How many grams are there in 1.5 times 10 to the 25th molecules of carbon dioxide? Okay, so what are we looking for? Well, we're looking for grams, so we're going to circle that. That way we know that's what we're searching for. And what do we know? Well, we know that we have 1.5 times 10 to the 25th molecules of carbon dioxide. Okay, we always want to start with the number in the problem. So to set this up, we would write out 1.5 times 10 to the 25th molecules of CO2. Okay, we're going to multiply this by a fraction. Since molecules is here, we're going to pull it straight down, and it's going to be on the bottom of the next fraction so that it will cancel. Well, we want to go from molecules to grams, but there is no direct path from molecules to grams because molecules would be particles. And we said that from particles you can go to moles, and from moles you can go to grams, from grams you can go to moles, and from moles you can go to particles. So I like to say, whenever in doubt, go to moles. Whenever in doubt, ... go to moles. Why? Because that will probably fix your problem. Okay, so let's go to moles. Well, let's put mole here and carbon dioxide there. And we know that in 1 mole of any substance there are 6.022 times 10 to the 23rd molecules of that substance. And look, molecules will cancel. And now we're left with moles. But we don't want moles, we want grams. So we're going to keep going. We're going to put moles on bottom because we want to get rid of moles of carbon dioxide. But we can go from moles to grams of carbon dioxide. All right. Well, in 1 mole of any substance, how many grams of carbon dioxide are there? Well, that's where you have to break down and figure out your molar mass. So there's, in carbon dioxide, there's 1 carbon and there's 2 oxygens. The mass of carbon is 12.01 and the mass of oxygen is 16.00. Okay, we do the math. 1 times 12.01 is 12.01 and 2 times 16 is 32. And then when we add that together, we get 44.01 grams per mole. So if we put 1 mole on bottom, we must have 44.01 grams on top. Moles of carbon dioxide will cancel and we're left with grams of carbon dioxide. And look, that's what we want. That's what we want to know. All right, so grams of carbon dioxide is our units. Units are good, so now what we do is we grab our calculator and we solve for the problem. So 1.5 times 10 to the 25th, 25, divided by 6.02 times 10 to the 23rd, and then we multiply that by 44.01. I think I might have done that wrong. Times. Okay, and the calculator gives us 1096.230488. Okay, but we don't want all that. We want 2 significant figures. So the 9 makes the 0 become a 1, so 1100 grams of carbon dioxide. Or you could do 1.1 times 10 to the 3rd. Either one is fine. So the next question says, what volume would the same carbon dioxide occupy at STP? Well, we have 1.5 times 10 to the 25th molecules of CO2. Because we're starting with the same thing, we can start there. You can start here. You can start at any of these. It really should give you the same answer. And we want to go from molecules to volume. All right, well, molecules are here under particles. How do we get to volume? Well, we can get to volume off of moles, can't we? We sure can. So we're going to multiply this by our fraction. 6.022 times 10 to the 23rd molecules goes on the bottom because we want that to cancel, and 1 mole goes on top. All right, multiply that by another fraction because we're not done yet. We want volume, not moles. So we're going to put moles on the bottom and we're going to put liters of carbon dioxide on top. Well, in 1 mole, we can have 22.4 liters. So moles cancel and we're left with liters. That's what we want in our answer. So we're going to put liters of CO2 for our unit. And now we solve 1.5 to the 25th divided by 6.022 to the 23rd times 22.4. And that should give us 557.954, and it gives us more, but we only want 2 significant figures. So this would become 560 liters of carbon dioxide. Pretty easy, right? Okay, what is the molar density? Now remember, molar density, we do molar mass divided by molar volume. And I told you the molar volume will always be 22.4 liters. So what is the molar mass of carbon dioxide? Well, we figured it out right here. So we take that number and we plug it in, 44.01 grams. And so now we just have to 44.01 divided by 22.4. And the molar volume is 1.964732 yada 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 grams per liter. And we have 4 significant I just lost my number. I just lost it again. Sorry. We have 4 significant figures on top and 3 on bottom, so we would just say that there's 3 here. So 1.96 grams per liter would be our molar volume. A lot of writing, I know, right? Okay. This right here is on your vodcast notes. It's just a little roadmap that will help you remember what to do and where to go. Just remember, whenever in doubt, go to moles. Okay? If you're ever in doubt, go to moles first and then find your way back. Make sure you leave breadcrumbs. Okay. And that's it, ladies and gentlemen. So I guess I'll see you in class.